Okay. Okay, in our last class, we discussed about nuclear fission and nuclear fusion reaction, right? In fission reaction, we discussed that when we split a heavy nucleus into two small nuclei that are more stable than the large nucleus, so that process is called fission, right? And in fusion reaction, we combine two small nuclei to make up a heavy, stable nucleus. So that process is called fusion reaction, right? So these are two different nuclear reactions that we discussed last time. And for fission reaction, we observe that how it actually works. We strike neutron into the nucleus because neutron is neutral and it can easily make nucleus more unstable. So it starts to emit out radiation more rapidly, and that causes fission reaction. Okay. Today, let's try some questions from the nuclear to revise the all previous topic. Because only one topic is left in this chapter, that is nuclear reactor, but that is, that is only the working of nuclear reactor. There is no equation, no formula for that. So today we practice the questions from the half-life, fission, fusion reaction, isotopes, Rutherford experiment, all the previous topics. Okay. So let's continue with some MCQs first. Question number one. A radioactive nucleus emits either an alpha particle or a beta particle, right? So there is a possibility for alpha and beta particle emission. Okay. Now, whenever they ask in question about emission, like in this question, they ask about nucleus emits. Emits means like to subtract the mass equal to the mass of alpha or beta from the nucleus. And now we all know that alpha is equals to 2He4, right? The mass of the helium atom. And for beta, beta is only -1, 0. Okay. So what are the products of these two types of radioactive emission? So you need to identify the products of these two types of radioactive emission. For example, if we consider alpha particle only, because there are two different columns. First column is for alpha, second column is for beta. So you need to consider both examples individually, right? For example, we have a nucleus. We have a nucleus over here. Right? And from this nucleus, there are two possibilities because in question it is mentioned either an alpha or a beta. So two possibilities are there. We are not sure. So the first possibility is for alpha. So we need to solve equation for alpha individually. And the other possibility is for beta. So you need to consider beta individually, right? You don't need to mix up alpha and beta in a single equation. You need to solve them individually. So first of all, if we start with alpha, so in equation of alpha, so what do you think? There are four possibilities given. In the first column, there are four options. A nucleus of a different element, like if we consider any element, for example, we have element, we are talking about alpha right now. And the values are, for example, 10, 18, right? So when this nucleus splits into alpha, 2, 4, right? So in result, what will be the mass number? What will be the atomic number of the element that we will get in the result with alpha? This is the initial product, X, right? And X is like any element having 10 number of proton, 18 number of nucleons. And from this element, we emit out alpha. alpha is equals to 2 and 4. And if you remember, we need to balance equation of both sides, right? So we need to balance the number of atomic number and atomic mass on both sides of equation. So what do you think? What will be the final numbers for this element Y? So we need to subtract these two values, 10 minus 2, right? It will get 8. 18 minus 4, it will be equals to 14. Okay. So
14.
yes, so this is the final result. This equation is just for your reference. This is not exact equation for this question, right? This is just for your reference. That's why I used to write X and Y. So now you can compare the number of atoms and the number of nucleons in the equation. So according to the equation, we observe that proton number also changes and neutron number also changes, right? Because we got 8 and 14. Initially, we have 10 and 18. So what do you think from these four options? The first option is a nucleus of a different element. So is it possible that we will get a nucleus of a different element in final result?
So
This
I
is
think yes, because
hmm, because both
after we
numbers
have
are
the
different,
yes, sir.
right? So we are getting both
Okay, sir.
numbers.
Over here, y is our
Hmm.
So why are we adding the beta and the y rays?
No,
The
there is
beta rays.
no beta is not there. We are only talking about alpha right
No,
now.
no, no. Yes, sir. Sir, I'm saying this. Why are we adding it? I actually forgot this concept. It's
Okay,
I got a bit confused here.
basically X is like uh the total nucleus, right? X is one nucleus only, right? For example, if you break a one nucleus or a heavy nucleus like nucleus X in our example, so if we break X into alpha, right? So let's suppose X is equals to 100, for example, and from that 100 value, we like subtract the mass of alpha, right? So definitely when you subtract the mass of alpha from that X particle or X nucleus, so in result you will get less than 100 value. Okay. Because alpha has its own atomic number and atomic mass. And when you subtract alpha from the main nucleus, so definitely we will get another element in the result. So that's why we are writing alpha plus another element. Okay. Because
Okay, sir,
alpha,
got it.
yes, alpha and Y, these are small nuclei. Okay. If you again combine them, it will give you the same result just like the X. Okay.
Yes, sir, I now got it.
Yes.
So, sir,
So
this was to find that what would be the state or the product after the emission of the alpha particles.
yes, you need to find out the final result, the final product after emission of alpha. Because alpha is understood. We know the values of alpha are confirmed. There is no change in alpha values. It always remains the same. But the final product depends upon the element that we are using, that how much number we are getting. So we are getting nucleus of different element, right? Because there are different numbers. Initially we have value 10, but right now we are having value 8. So it is different. Initially we have 18, now we have 14. So it means we got a different nucleus of different element. So A and B, both statements are correct. C and D are not correct only for alpha, right? We are only talking about alpha. Okay.
Okay.
Now, if we consider beta, so for beta, we need to perform the same process again. So for beta, again, let's suppose we consider the same element X, 10, 18, -1, 0, right? So what will be the final result for this nucleus Y? If you remember, we discussed in beta decay or in beta emission, there is -1. So due to this -1, we will get additional sign over here. You need to just perform calculation like the previous one. Like in previous alpha, we subtract 10 minus 2, right? So if we again subtract 10 minus -1, okay, because there is already minus 1 minus for the formula, 1 minus is already with the beta. So 10 minus and -1. So minus minus will be plus. We will get value 11. Okay. And there is no change in the nucleon number. So nucleon number remains the same, right? So now what do you think about beta? Beta also gives you a different nucleus or the same nucleus? It also gives you different one, right?
Yes, sir.
Because the numbers are different from the initial one. So it means option A is correct because this statement is not correct and this statement is also not correct. So there is only one possibility, that is option A. That in both case we will get different product after alpha and beta decay, right?
Yes, sir.
Okay. Question number 2. Question number 2 is related to the half-life. A reading is taken every 10 minutes. So we are recording the reading after every 10 minutes for the number of emission per second, just like count rate per second from a radioactive source. The table shows the reading. So what is the half-life of the source? So how to identify the half-life? Yes, any question? Rayan. Yes, Rayan, any question or
Sir,
yes?
I want to ask that we when they mean that what is the half-life of the source, it means that how much time it has taken them.
Yes. Because you can see all options are
So
already given in time. Okay. So the process of half-life is very simple. What is the initial value given in the question?
800.
800 is the initial value. And to find out the half-life, what you need to do with this initial value? Half-life means to divide the initial value with 2 to decrease the mass into half. 800 divided by 2 will be equals to 400, right? And you can see 400 is given in your table already. So it means the time for 200 is the time for your half-life.
Sir, instead, I just want to clear this.
Hmm.
Okay, okay, so I got it now.
Right? So always remember, whenever we solve the questions of half-life, we consider initial value. We divide into 2 because of half-life. And sometimes the targeted values are given. But in this question, targeted values are not given. They just ask general question, what is the half-life? Because values are already given in your table. The values of time, the value of number of emission. So that's why we just perform one half-life and we got a value 400 and we identify from the table that what is the time for the number of emissions 400. So that is 20. Okay. So 20 is the answer. Yes.
Sir,
Can you like scroll up a bit? I just want to see the answer for the question number one.
Option A.
Okay, sir, I got it.
Okay.
You
So
can
these
scroll
are
down now.
so these are two questions related to the basic concepts that we already discussed in this chapter, but we need to revise, we need to practice these questions so that it will be easy for you to solve unknown questions for the first time. Okay, graphical representation. Okay, the graph shows how the decay rate of a radioactive source changes with time. In the previous question, we have a table, but now in this question, we have a graphical representation, right? So both gives you the same concept, the number with respect to time. Question is, what will be the activity? Activity means you remember the word activity. Activity tells you about the number of emission per unit time, the same definition. Okay. In short, they are asking about the half-life, right? After 8 days. So activity is the same term. In notes, you can find out the word activity. You can see activity is the rate of radioactive emission from the sample, right? Or number of radioactive radiations emit per unit time. So it is the same thing. Number of emission per unit time. So this value is 4. It is misprinted. 6, 8, and 10. So now what will be the activity at 8 days? So there is graphical representation, and from that graphical representation, uh, initial value is given. So whenever we are performing half-life for any element, so always remember that we need to start with the initial value. We need to perform half-life to get the targeted value. So now in this question, you got your targeted value. Your targeted value is 8 seconds, right? So try to perform half-life for this question.
Sir, we will divide 4,000 by 2.
Yes, because graph start from the value 4,000. So we need to divide 4,000 by 2. So you will get value 2,000, right? And it,
Yes, sir. And it is falling at 2,000 by at 2 days.
yes. So from graph, we can identify that the value 2,000 is exactly at 2 days. Okay, I will share the notes again.
Sir, is it possible if you can send the PDF form so it is easy to take the printouts rather than noting them down?
For notes or for this?
Sir, the notes.
Okay,
The notes that are pre-written.
okay. I
Those.
will share that notes again in the group.
Thank you, sir.
Okay. So we performed the first half-life, we got the value 2. Now we need to perform half-life again. And one thing you identify from this graph that the half-life of the element is for 2 days only. Because in 2 days, we will get the half value of the initial one. Okay. So 4,000 divided by 2. This is the first half-life. Again, if we perform the half-life, you will get 1,000. Okay. Initially, we consume 2 days, right? Then 2 plus 2, 4 days. After another half-life, it will be 6 days. And the question is for 8 days. 8 days is your targeted value actually in this question. This is your target. So after 6 days, we got the value 500. Now 500 divided by 2 equals to 250. And after how many days?
8 days.
8 days, right? So it means after 8 days, we got the value 250. Okay, option C, right? So this question is very simple. Just to confuse you, the graph is given in the question, but from the graph, you just need to take the initial value or the initial half-life for the radioactive sample, and then you just need to perform the half-life by dividing 2 again and again. And after 8 days, you will get your answer, which is equals to 250. Okay. Okay. Question number 5. Again, we have a sample of radioactive isotope with initial rate of emission. So it is already given in the question initial rate. So initial rate is given 128 counts per minute. And a half-life of 4 days. So half-life is also given. How long will it take for the rate of emission to fall to 32 counts per minute? So now this is your target. You have to reach this value from the start because initially we have 128. And after every 4 day, this mass decrease into the half of its original value. Okay. So how to find out the number of days that will take for the rate of emission to fall to the value 32 counts per minute. So try by yourself also to find out this number. Yes, Afan,
Sir, 2 days?
2 days. Okay. But you can see half-life is of 4 days. For example, it is like this. 128 divided by 2. It will be equals to 64, right? And how many
Yes,
days
sir.
it will take? 4 days.
4 days.
Yes. So this is the initial half-life. This is the first half-life because it is given in the question. So after first half-life, you got answer 64. Actually, you said that 2 days. That is not 2 days. That is after two half-lives, right? Because if
Okay,
you,
sir. Sorry.
yes. So if you perform again half-life, you will get 32. 32 and 4 plus 4 equals to 8. This is your second half-life, right? So your answer is correct in numbers, but unit that you use is different. So after two half-life, we reach our targeted value. Okay. And
Yes, sir.
after two half-life, total we consume 8 days to reach the value 32. So answer is 8 days, right? So this is a simple question also. Because targeted value is given, initial value is given, you just need to start from the initial value and reach the targeted value given in the question to get the final result. Okay, we already solved the basic properties. Question number 9. Now try question number 9 by yourself also. It is also related to half-life. It is very easy. This is initial value. This is the targeted value. Okay. And half-life is given. So you need to find out the mass of the isotope remains after 10 days. Yes.
So
Sir,
part C.
40 mg.
sir, answer is C.
C.
C. Okay. Right. So part C is the correct answer because it is very simple. Initially, we have 400 and it is written half-life is of 5 days. So after 5 days, we got 200 value like this. And if we perform another half-life, so we'll get value 100. And why we perform two half-life? Because half-life is of 5 days. This is the first half-life. And then we have 10 days, second half-life. Okay, so target is achieved 10 days. And the value we are getting after 10 days is equals to 100. Okay, simple. Okay, question number 11. So question number is 11 is slightly different because it is included the background radiation. So in a laboratory, a detector of ionizing radiations records an average background count rate. Background count rate means some radiations are already exist in our atmosphere, in our surrounding. Okay, but those radiations are not harmful. Just like we discussed, we are getting radiations from the sun. Okay, so radiations from the sun are already in our surrounding, but those radiations are not harmful. Radiation from the rocks, radiation from the building, because we are using different devices nowadays, digital devices. So like microwave oven and all the heating devices, so they are emitting different type of radiation. So these radiations are already in our surrounding, but these radiations are not harmful. So this 8 counts per second is the background reading, right? This is not radioactive, this is only background reading. Okay, these are not harmful. Now in the second paragraph, a radioactive source. Now we place a radioactive source close to the detector and the count rate on the detector rises to 200 counts per second. Okay. So what is the actual value of the radioactive source, or what is the actual value of the count rate for radioactive source, not the background?
Sir, we'll subtract 200 by
Yes,
8, getting us the answer 192, meaning part B.
Yes, sir. Same.
right. So you can easily identify that background reading is already 8 and the detector gives you 200 reading after placing the radioactive material. So 200 minus 8 equals to 192. So answer is 192. Okay. The same question they ask in this 11. Question 13. Again, we have a radioactive source produces a count rate on a detector of 1600 count rate per second. We have a radioactive source. On detector, we are getting 1600. After 32 hours, the count rate has fallen to 100 count rate. So this is a different type of question. Both count rates have been corrected for the background radiation. It means there is no background radiation. What is the half-life of the source? So this is your initial value. And we know that we have to start from initial value. We need to perform half-life. And after performing the half-life, we need to reach this value. This is our target. Okay. Because you can see 1600 is greater than 100. So it means we have to start from 1600 and then decrease the mass again and again to reach the value 100. Okay. So let's start from 1600. And let's see how long it will take to reach the value 100. Okay. So starting from 1600 divided by 2 equals to 800. Again, another half-life, 400. Another half-life, 200. Another half-life, 100. Right? So in this way, we reach the targeted value given in the question. Okay. And how many half-lives we perform in this question to reach the targeted value? This is the first. This is the second. This is the third. This is fourth. Right? So how many half-life we perform? We perform total 4 half-lives. And there is one more value given in the question, that is 32 hours. So this is not the half-life, this is the total time given actually. So in 32 hours, how many half-life we perform?
Sir, 8 hours.
8 hours, okay. So it is very
Sir,
simple. Hmm.
as to your question, we did 4 half-lives in 32 hours.
Yes. So we utilize these 32 hours to perform 4 half-lives. So 32 divided by 4. It will give you the time for 1 half-life. That is 8. So in 8 hours, we perform 1 half-life. Okay. So you can see this is another pattern of the question related to the half-life, but the process remains the same. We consider initial value, we consider targeted value, we perform half-life, we reach the targeted value, and then we just need to sum up your question according to the values given in the question. Here, any confusion? Okay. Question 16. And you can see there are so many questions related to half-life. Like every second question is from the half-life topic. So a radioactive isotope is placed near a detector. Again, radioactive isotope placed near a detector. The readings on the detector are corrected for background radiation. So there is no background radiation. And it is recorded every hour. Like after every hour we recorded these values. Now what is the half-life of the isotope? Okay. So try to figure out the half-life from the given values in the table.
Sir, after I'm done with the doing the first half-life, I'm getting the answer 250.
But that is not in the table, right?
Yes, sir. And if I do it furthermore, then I'm getting the answer 125, which is also not there, but
Not
it
in the
is,
in between.
yes, it is in between the 210 and 160, which is between the third and the fourth hour.
Yes. So this is the thing. Because options are now this time we have different options. We have options between
Yes,
1
sir.
and 2 hour, between 2 and 3 hour. So, but process remains the same. After first half-life, we got value 250. So we need to identify where is 250. So 250 lies between these two values, right? So 250
Yes,
is in between 280 and 210. That means between 2 and 3 hours. Okay. So in this question, the exact value is not given. the estimated values are given. So according to the estimated values, the answer is between 2 and 3. Okay. Question number 17. A student investigates how the radiation from a radioactive source changes with time. The table shows the result from the detector used by the student. The experiment is repeated by many other students who also measures the count rate every 2 minutes. So count rates are recorded after every 2 minutes. The half-life of source is exactly 2 minutes. Why is the measured count rate always greater than the half-life of the previous value? So in the table, you can see that initially we have 340, right? So if you divide 340 by 2, you will get answer 170. But we are getting 180, right? And again, if you divide 180 by 2, you need to get 90. But we are getting 100. And same for 100, if we perform half-life, the value will be 50, but we are getting 60 again. So we are getting always 10 numbers greater as compared to the previous one. Okay. So what do you think? Why we are getting always 10 counts rate per minute greater than the original value? This is the question.
Sir, I think it's the answer is C because there is background radiation
Yes.
present as well.
Right. So
Same,
C
sir.
is the answer because we are always getting 10 value greater. So that 10 is actually the background reading.
Okay, so should we like rejoin?
Yes.
Okay.